Okay, sir. I'll introduce the speaker to the participants. It is our pleasure to welcome Dr. Anirban Roy, Head of Department of Assam University, Diphu Campus. We are glad to have you here, sir. And please start the presentation.
So good evening to yes, please, sir.
The duration is 60 minutes, sir.
Okay, sure.
Okay.
So I think good morning to everyone present on this RIST workshop on International Year of Quantum Science and Technology. It is my pleasure to give a talk on this occasion, and I thank Professor Nimai Singh and all other person who cordially and kindly invited me to give this kind of talk in front of some audience. Although this subject is old, but still I find that in most of the Indian universities, quantum mechanics is not taught in this way, starting these properties of quantum mechanics and all these things, where we generally don't go into solving the Schrodinger equation and all these things, but rather we try to understand quantum mechanics from its basic. So without any further delay, let me start this talk, which is basically this quantum entanglement I'll be talking of. But before that, I would like to say a few words, like when quantum mechanics initially started, actually it is counterintuitive to all our daily experiences, because we had something called a uncertainty, something called complementarity, which nowadays even called in terms of no cloning. Basically the thing is that in classical world you can discriminate among all the states, you can clone all the states, but in quantum mechanics, unfortunately or fortunately, these things are not possible. Like, you can only discriminate states that are orthogonal to each other, but you cannot discriminate states which are non-orthogonal to each other. And this is actually the famous no cloning theorem. And even why this happens? Because in quantum mechanics, unlike in classical mechanics, we allow something called superposition of states. So you can have a state like, say, 0, which is a spin up state maybe, and a state which we call, say, 1, which is a spin down state. Then you can have a linear superposition of these two states, which is not allowed in classical mechanics. And from this simple thing, many interesting features started. So I just, so this is the outline of this talk. So I'll be just considering the definition and properties of entanglement, and then I'll be defining something called local operation and classical communication. And then we'll be just behavior of entanglement under LOCC, and then this use of entanglement in some practical scenario. So for that, first we have to define what is entanglement. Now, we all know that this is some kind of particular type of correlation, and mathematically this correlation is given by this particular format. Like for entanglement, at least you require 2 or more systems, but for the sake of simplicity, I'll be just confining myself into two particle systems. So basically 2 parties are there. They can share an entangled state, and this entangled state they will be sharing if this entangled state cannot be written as in this particular format, that rho AB, where rho AB is the state between these 2 parties, say A and B, which generally historically are called the Alice and Bob from the beginning. That's what we'll be mostly calling them, an Alice and Bob only. And that cannot be written as equal to the summation of I, omega I, rho AI, and then O times rho BI, where basically this omega I, this is the weight factor, all the omega i's has to be greater than equal to 0, and the summation of these omega I has to be equal to 1, and then rho I A and rho I B, they are the states of system A and system B respectively. Now the thing is that although it seems very simple, but in most of the cases, given any particular state, whether that state is entangled or not, it is very difficult to say. But because if the state is, because the state that I have written on the left is a general state which is basically called the density matrix. So, and but if this state may not be a pure state, pure quantum mechanical state, because we are more familiar with the pure quantum states. So I am just writing an example of a pure entangled state between two systems. And for pure state, things are simple, that you cannot write a state of an entangled system by just merely taking state of one system and taking state of another system, another pure state of both the systems, and then you just merely join them, and then you cannot have the entangled state. And I have given an example of this entangled state. It is basically this phi AB, which is 1 by square root of 0 of state A and 0 of state B, and plus 1 of state A and 1 of state B, where I have mentioned these 0 and 1 are eigenstates of the Pauli matrix sigma z with eigenvalues plus 1 and minus 1 respectively. And if the state is only written as 0 A and 0 B, but this 1 A and 1 B is not present there, then that state would have been not an entangled state. Now, let me just give that why this entanglement is so interesting to do. Because there is something called local realism, and it is a contradiction with local realism. I will not go into very details, because historically this local realism and this contradiction of entanglement with local realism is given by John Bell, which is famously known as Bell's inequality. But I will not go there, but I will give a much different proof, which is later on given by Lucien Hardy, and I will be just telling that proof here in short. So you can have, say, two system, and if each system is a two-level system, that means either system will give +1 or system will give -1 as the result when you make any observable on the system. So the first system, this is measuring observable A1 or B1, and it is completely up to dependent on the party 1. So he or she can measure either observable A1 or observable B1 at his or her own choice. And similarly, this party 2 can measure also two observables, and they are measuring these independently. They do not have to communicate with each other with anything, that I am measuring A1, you should measure A2 or like that. No. And the eigenstates of these observables I am giving as plus and minus corresponding to the observable A, and similarly I am giving these O plus and O minus, they actually correspond to eigenstates of observable B. And then what we are defining is that we'll be defining some joint probability and some conditional probabilities of these systems. So this probability is given, this P psi is the probability that both these O minus of party 1 and O minus of party 2, this probability is greater than equal to 0. That means in some experiment, if you perform, there is a possibility that both the parties, when they measure this observable B1 and B2, they can get both O minus. And then these are the conditional probabilities, the second and third, which is that if one gets O minus, then probability of getting minus is 1. I have written these things. And then if one other party gets this O minus, that means the second party gets O minus, then probability of getting this minus is 1. And so, but the joint probability of these minus getting both the parties is 0. So what does this means? This means, sorry, yeah, that we are doing a run of experiment, and then suppose the first probability that it is a probability 0. Now consider these two parties can be far different distance away from each other, and they are not communicating. So suppose if the party 2 is not measuring B2, but he is intended to measure A2, then as party A is already getting O minus, then party 2 definitely would have get this minus of if he or she measures A2. Similarly, the other scenarios is also happening, that instead of party 1, if instead of B1 he or she wanted to measure A1, then she would have been definitely obtained minus, because party 2 has already, he has obtained B2, he already obtained result O minus. So basically then what happens, that both parties should obtain, there is a probability that both parties can obtain minus. But see, the problem is that this is what I meant to say, that if instead of B1 and B2 both parties have measured A1 and A2, then they should have obtained minus in both their cases. But you see on the left hand side that probability is 0. So this is basically the simplest way of considering that entanglement in something which contradicts local realism. Now the moment we consider that this entanglement they contradict the local realism, then we have to find out that whether there exists a state in quantum mechanics, a valid quantum mechanical state which satisfies these probabilities or not. And it is interesting to find out that really there such kind of state exists. So this state I have written that this is a bipartite two-level quantum mechanical valid state, and there it is A plus 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 B plus minus, then and plus minus plus, as you can see from the slides. And where A is given as cos theta and B is given at sine theta by square root of 2, so that I have to make this psi 1 2 is a normalized state. Remember, in most of the times whenever we are discussing here, we will be always talking of normalized states. And then we can define that these O plus for both the cases and O minus for both the cases by giving the relation with the plus and minus states by this. And you can understand that this O plus and O minus, they are actually orthogonal to each other the way we have made it. And these plus and minus, these are also orthogonal states. So now I can write this psi in this new basis also in this fashion. So now if you do, you can always find out that all these probabilities that we have defined in the previous cases to show that there may be a contradiction with local realism if such a quantum mechanical state exists for entangled states. And so this state is given by I have already given the state, and then these probabilities are given by these values. So you can see that the first probability is greater than 0, but the only condition is that this theta value that we are taking, that theta value cannot be equal to 0 or cannot be equal to pi by 2. And all other probabilities are there. And this probability, this will be maximum for this value of theta, which is 60.9 degree. So now some properties of entanglement is that we consider this is an expensive resource and it cannot be created among distant parties, but once it is created, parties can share it at any distance. So if the two parties are situated at distance, these parties, they cannot create any entanglement among them. So to create the entanglement, the parties either has to come together or some third party has to create it and send these entangled state sharing between two parties or more parties. But the important thing is that it cannot be created among distant parties if the parties are situated at distant locations. And now, once this entanglement, shared entanglement is given at distant locations to two parties, the allowed operations between all these two parties are something called a local operation and classical communication. Because what they can do, they can make any quantum mechanical operation on the particle that they have in their possession, and they can, after the measurements, whatever results they get, they can communicate over some classical channel like telephone line among themselves. So these type of operations are called LOCC in short. And the most general form of LOCC is not known. This is an important scenario, that although we know that the parties which are at distant locations, they can make only some kind of LOCC operation, but any general form of this LOCC operation is not known. So we have something called as separable operators, which is given by this particular form, that summation over I, AI, and cross BI. This is O times BI, where AIs and BIs are positive operator valued measure called POVM in general. I'm not going into details of these. And operators on A's Hilbert space are positive semi-definite and complete. And similarly for the BIs on system B. So positive semi-definite and complete means this is that all the AIs has to be greater than equal to 0, and summation over I AI has to be is equal to identity, because these are operators. So if you sum them, they have to give you identity. But this is the condition that we have to give, because to preserve the probability. And now, as I have in the beginning, I have mentioned that there is something called a no cloning. This no cloning theorem that states that non-orthogonal states can never be distinguished with certainty, but orthogonal states can always be. Now the scenario is, when I'm talking of orthogonal states, these orthogonal states can be of entangled states also. And when these orthogonal states are entangled, and these entangled states are, say, multipartite, and these parties are at distant locations, then as we have already discussed, there's only LOCC operation is allowed as operation. Then for those scenarios, this distinguishability of these orthogonal multipartite entangled states with certainty is not allowed. So why it is important again? So suppose you want to make put some data into these orthogonal states, so some bits of data, and then you put these orthogonal states shared at distant locations. So unless all these particles come together, they cannot retrieve that data, which is important in preserving some important data. That only when all the parties come together and they mutually agree that, okay, we will be retrieving their data, then only the data can be retrieved. Otherwise, these data cannot be retrieved. But the thing is that if you have two orthogonal multipartite state, then distinguishability with certainty is always possible with LOCC. So this I am not going into details that how to do that, but this can be done. This is already shown. So this is not our concern, but what we are trying to do is that, say, instead of two states, let us take four orthogonal states. And these orthogonal states we will be defining, they are actually called maximally entangled states or Bell states, which we know as another way that they are famously called the triplet and the singlet state. So the last state before that is the singlet state, and B1, B2, B3, they are actually the triplet state. But in terms of quantum information, we talk that these are Bell states because they actually the Bell inequality, these states, they uh, by maximum value, they give the Bell inequality values. So that's what these are called, Bell states. But now we'll be putting in our original questions that can this be distinguished using LOCC? So as we already told that mathematical form of LOCC is not available. So, but there we will be using some different properties of entanglement to check the distinguishability. So one property of entanglement is that it cannot be created by using LOCC. So suppose we take it in the opposite, that it is possible to distinguish the 4 Bell states using LOCC. So then basically what happens, suppose we have now 4 parties instead of 2 parties, and the Bell states, they are shared between these 4 parties in this following format. That these 4 parties we define as Alice, Bob, Claire and Danny. And then this Bell state, you can see that this Bell state, it is basically given by this particular way, such that the state itself is telling that between AB versus CD, the state is separable. So you cannot create any entanglement between Alice Bob versus Claire and Danny. So the between Alice Bob and Claire and Danny, there you, as this is a separable state, so whatever you do, you cannot create any entanglement between them. Now we consider that these 4 Bell states are locally distinguishable. So what Alice and Bob they do, that they without meeting, they can just consider that which of the Bell state they have, because I already told that this is locally distinguishable when we have considered this condition. So the moment it is known that Alice and Bob says they share as B1 as a state, then they just put a classical communication to Claire and Danny, and so Claire and Danny will be also having known that they are having a Bell state B1. So this is understood and not a big problem on these things. But now interestingly, this particular state also can be written in this particular format. So what we have considered in the previous cases, that Alice and Bob versus Claire and Danny. But now I can make it, the same state can be written as between Alice and Claire versus Bob and Danny. And that is also separable between this cart. So Alice, Claire and Bob, Danny cart is also separable. But now we have also already considered that Alice and Bob, they are able to distinguish between them which Bell state they are sharing without meeting, only by LOCC. And immediately Claire and Danny, they will be saying that they are having this state, one of the Bell states. So between Claire and Danny, there will be an entanglement is there. So although these 4 parties are at distant locations, they are not meeting, only by making the operations on their side and then communicating the classical results, they can make to share some entanglement between Claire and Danny. That means between AC and versus BD cut. But this is already that cut, the state is separable, and we told that entanglement cannot be created. So although we do not know the exact form of this LOCC, but using just a property of entanglement, we can already tell that these Bell states cannot be discriminated, because otherwise that will uh, contradict one of the famous property of entanglement, that is entanglement cannot be created between distant parties if they are only allowing LOCC, that is local operation and classical communication. So in this scenario, it can be understood that it is not possible to locally discriminate among these four Bell states. And then again, this is one of the properties of entanglement, that not all entanglement cannot be discriminated, although these entangled states are orthogonal to each other, but by only using LOCC, they cannot be discriminated. And as I already mentioned, one of the uses of these is that to keep some secret data shared among distant parties, where unless the distant parties come together, they cannot retrieve the data. And then another important phenomena is basically quantum teleportation, where also we can use entanglement and local operation and classical communication. So so this is the scenario. So now what we will be doing, this is what basically the scenario, that there are two parties at distant location, Alice and Bob. They share some entangled state, and then Alice was given an unknown quantum state, and as the state is unknown, so there is no way Alice will know what state is given to her, but her job is to create the same unknown quantum state at Bob's end without transforming the particle or without sending the particle itself. And how do they do it? And this is called a teleportation from some movies. The name is taken, and then we have used this as quantum teleportation. So same name we are using here. So basically we have that an unknown quantum state psi, this is held by this party Alice, and she wants to send to this another party Bob without transforming the physically transporting the state. So for that, they will be requiring an entangled state, and this entangled state has to be a maximally entangled state. I am not going into give you that why if do not share an maximally entangled state, it can be shown that this teleportation of these particle of this state is not possible, but I'm not going to prove that. And as Alice and Bob, they are at different locations, so only LOCC operation is allowed. And so Alice only can make some measurement on the particles she held. That is, she has two particles. One particle is the particle on which the unknown state is given, and another particle is one particle of that entangled state, because entangled state is of two particles. One is at with Alice, another is at with Bob. And after this, Alice make these measurements on her particles, and upon receiving the measurement results, she can communicate the measurement results to Bob, and accordingly Bob has to do some operations on his particle to retrieve the unknown state, and we'll be showing that how that can be done. And this is basically the quantum state that we are considering. This is given by 0, 0 and 1, 1, and these zeros and ones, they are nothing but the eigenstates of sigma z, which is a Pauli operator, as we have already told. And then this Alice, she holds an unknown state psi, which is given by alpha 0 plus beta 1, and alpha or beta are unknown, as we have already told. Because if alpha beta had known, then she could have just communicated this alpha beta to Bob, and then Bob would have known that what state Alice wanted to send to her. But interestingly, Alice does not have any idea on of this alpha and beta, and Alice, in there is no way Alice can gain any information on this alpha and beta because of this non-discrimination or no cloning, whatever you call, theorem. And as I have told that Alice can perform a measurement on the particle 1 and particle A together because she has those two particles under her possession. And so now Alice has to make a measurement, and we know that if you do a measurement operator, the measurement operator being an Hermitian operator, it will have eigenstates. So the following eigenstates are there of this particular measurement operator. And these are the eigenstates. These are again the same kind of Bell states that we have defined, but now I'm defining these as phi plus phi minus psi plus psi minus, because these are the known representation of these states to us, where you understand that these psi minus is that singlet state, and these phi plus phi minus and psi plus, these are the triplet states. So after the measurement, Alice receives one of the four above states and then communicate these results to Bob. And then if Alice gets phi plus, then the state is magically psi appears magically on Bob's particle. But if Alice gets phi minus, then Bob's particle has the state alpha 0 minus beta 1, and making an operation of sigma z on Bob's particle, which keeps state 0 as 0 but changes state 1 to minus 1, the state psi reappear at Bob's end. Similarly, if Alice gets psi plus, Bob's particle state will be having alpha 1 plus beta 0. And now making a sigma x operation of Bob's particle, which changes state 0 to state 1 and state 1 to state 0, then makes psi reappear at his end. Similarly, the final one, if Alice gets psi minus, because remember one thing, there is no way Alice has any control of which output he will or she will get. Because all the four states, phi plus, phi minus, psi plus, psi minus, that appears at Alice's end after this measurement operation, they all have the same probability. And Alice will have no control of which state she is going to get. So she has to be prepared that whatever state she is getting, Bob's particle state should be able to change to the state psi, which is the unknown state that Alice wanted to send to Bob's end. So in these final cases, the operation is minus sigma x, sigma z. And so basically that does state 0 goes to state minus 1 and state 1 goes to 0. So this is how the state will come up. I have not written the entire state as a whole because that will look slightly clumsy. So I have not done. But as I am telling again, by teleport a state exactly, one requires a maximally entangled quantum channel. But this is for a single quantum state. But now what happens if we have an entangled state shared between two parties, which will maybe calling them as Alice 1 and Alice 2, and then we will be using two quantum channels to send this state to another two parties, Bob 1 and Bob 2. And so these are the, as I have again here in this scenario, what I will be using, I'll be using a non-maximally entangled state. And there, using this non-maximally entangled state, this quantum state, this cannot be teleported exactly, but we have to find out that how much teleportation, how much entanglement you can have. So let me go and give you this basically idea, that this is the basically the idea, that as I am telling that there are two parties, Alice 1 and Alice 2, and they are sharing some entangled state, say phi 1 2. This phi may not be a maximally entangled state, it is something. And then they wanted to, they both of them, Alice 1 is sharing with Bob 1 a quantum entangled state, but that quantum entangled state is not a maximally entangled state. I'll be calling this quantum entangled state as rho Bm, because that is something called a Bell mixture. That is a mixture of Bell states. So instead of taking the Bell states by themselves, let us see that what this mixture of Bell states can do. Because we know in most of the time in quantum mechanics, although we do not tell it, most of the time we do not get the pure entangled state because of various factors. One of the main important factor that actually is there is that it's reaction of the entangles of quantum states with the environment, and because of that many times the entire quantum mechanical pure state loses its purity and becomes a mixed state, because that is what practically happens. Okay, so this is the basically the idea, and this is what we have to do. And then we will be using but as we are not sharing the maximally entangled state, so what type of teleportation protocol we'll be using? Now we'll be using the teleportation protocol as the itself is as if we are having a maximally entangled state shared between two. And already I have shown you that this teleportation protocol, already I have shared with you the teleportation protocol. Now, as the state is not exactly teleported, the input state is not exactly teleported. So there are two important factors to be here to be considered. One factor is called the fidelity, which is that how close the output state that is getting after this teleportation through this non-maximally entangled state, and then that mathematically that fidelity is given by taking the trace of the input state that we wanted to teleport and the final output state that actually is received at the receiver's end. And then what is the change of entanglement that is happening, that how much entangled state is the original entangled state is having phi, and what is the entanglement that is the output state sigma 1 2 is having after this teleportation by non-maximally entangled states. And the difference between this entanglement is called the change of entanglement. So this is the important thing that one has to consider. And so basically this is what we are considering. I am telling that this channel, this teleportation channel is considered to be the mixture of Bell states. So what do we mean by that? We mean by that this is the state, that it is the mixture of state psi plus and mixture of state psi minus. And the psi plus and psi minus already you know this is given to be there. And the state to be teleported is given by this particular factor. So state to be teleported is alpha 0 0 plus beta 1 1, where remember these 1 and 2, these two particles, they are shared to Alice 1 and Alice 2 respectively. So I am not going to show you the entire calculations because this we have already done it. And so after teleportation, the output state will not look very nice. This will look something similar to this, which is becoming shared now between Bob 1 and Bob 2. And interestingly, although this state looks like these kind of complicated ones, but these states, it remains entangled unless this W is equal to half. And this W has come up from this W, that this weight factor W, this W is the same as this W that is coming here. And remember, when this particular W here it becomes half, the channel itself is not anymore entangled, because then the channel is becomes a separable state. So both the Bell mixture becomes separable. So that is and if it is a separable state, then we cannot transform any entanglement between them. So interestingly, unless the channel itself becomes separable, after teleportation, the entanglement of the output state remains. And now the question that we are trying to put, that this fidelity and this change in entanglement. So the fidelity value is become this 1 minus 8 W into 1 minus W and mod of alpha beta square. So this is becomes the out fidelity, and this has already we have been calculated. I'm not going to through the entire calculation process. And then the change of entanglement is given by this factor, where this lambda plus and lambda minus, they are given by this one. So it is slightly complicated, the terms, but it is ultimately, this is the way you will be getting. So here important thing is that we can show that if you are not sharing a maximally entangled state as a teleportation channel, because keeping the maximally entangled state is difficult, but suppose we are not keeping some kind of non-maximally entangled states, but still we can teleport some amount of entanglement, although we cannot teleport the exact entanglement, but we can still teleport some part of entanglement. And we can also calculate the fidelity and all these things. And we have to find out that how to make this change in entanglement to be minimum, and fidelity has to be how much fidelity we can keep. So it will all depend on, as we can see in the fidelity, that it depends on this value of alpha beta and this W, definitely. And as we can understand that the closer we get the output state to the input state, the entanglement between input and output becomes closer. So this is only this is another important issue, and this should have been expected also. And okay, let me see. Okay, I have 15 minutes. So I'll be just doing one use of entanglement by in the field of cryptography. So this is cryptography is the art and science of achieving security by encoding this some message and send this encoded message so that this looks garbage to anyone in between, but to the receiver there will be some process of decoding by which he or she can decode and get the what is the original message intent to send to him. So I will just tell you that there is something called, in classical mechanics we all use the cryptographic everyday life, because the moment we say do some bank transfer and we log into the bank's website, or we when we go to the ATM and punch our cards through the ATMs and get the money back, these all require some kind of cryptographic protocol. The thing is that there is no classical cryptographic protocol exist which is in principle not to be remain secret, except there is something called a one-time pad. So because but the use of the one-time pad is very problematic, because the cryptographic encoding key every time has to be used is different, and that cannot be done, because say for example that means for every time, for every user to the sender, there has to be a private key, and that private keys can be used only once. But that is not in general possible. So most of the times in the cryptography, what happens, people use one kind of key, that those are called the public key, and that has been used, and it is used so that it is considered that the classical computers may not be able to crack them easily. But they are provably, all the classical cryptographic protocol except these one-time pad, as I am mentioning, are provably that they can be breakdown. So there will not be any classical cryptographic protocol that is secure. But we can use using these quantum mechanical uses. So I am just omitting these general cryptographic thing. So I'll be just going to the quantum protocol, that how quantum cryptography is provably secure. That is, there is no way, forget about whether we have that technology in future or not. Even if you have the few technology also, there will be no way in this quantum cryptography, if this quantum keys that is generated, that can be breakdown. So they are provably secure, and that is what people will be in future trying to do, that using the quantum cryptography to all these secure message uh, relay from one say party to another. Now, the famous cryptographic protocol that was there is given by Bennett and Brashard in 1984. It is called the BB84 protocol, and that is, interestingly, that was given in a conference held in Bangalore in India. But at those time, 1984s and all these things, things were not that very popular, so people did not give much importance or much hype to that. But that was the first time it happened, and it was a very interesting one. But what here we'll be using, we'll be not going to that thing. We'll be using here by using the quantum state. Sorry, the quantum entangled state. By sharing the quantum entangled state, how this can be achieved. Because in BB84 protocol, I am not going into details of that. There was no entanglement involved. So this is a scheme that was designed by Eckert. They are at distant locations, and they share many number of maximally entangled states. And say, for example, we are, for the time being, we are considering consisting of two photons, such that each of them hold one of the two photons. And this is the state that is there between them, and many such states has been shared. It is not a single state that has been shared. And then to establish the key, what they are doing, this Alice and Bob, they agreed beforehand some preferred measurement basis whose outcome is 0, 1, and started performing measurements. So remember, here we are not considering that these zeros and ones are of some particular preferred measurement basis. And we have used these state psi minus, which is basically a singlet state. The interesting part of this state is that whatever basis you use, like whether you use a sigma z basis, whether you use a sigma x basis, sigma y basis, or any basis which is directed in any other direction, the state can be always written in terms of 0, 1, minus 1, 0 in that particular case. That's what we have used this psi minus state. So that basically the thing is that whatever basis you use, the results are always perfectly anti-correlated. That if Alice gets 0, Bob will always get 1, or if Alice gets 1, Bob will always get 0. So that Alice knows on measuring her on her particle, after the measurement result she gets, she will definitely know what will be the measurement result of Bob. The only thing is that Alice does not have a control of her outcome, that either she will get 0 or she will get 1 in that particular basis. That probabilities, both of the probabilities are half. But the moment Alice gets either 0 or 1 on her state, she will definitely know that what is the Bob's result. And as I am telling, they are all perfectly anti-correlated. And what is happening that they can translate this result -1 to bit value 0 and result +1 to bit value 1. So this is they have agreed upon in the beginning. And remember, this is not only known to them, this is known to every other one. That if they are making a measurement and if she obtains plus, she will know that she will be assigning the bit value 1, and if she obtains -1, then she will be assigning the bit value 0. This is known to everyone. That does not make this to other parties to know that what, because they will not communicate their results. They will just communicate that what measurement basis they are using. That is also known. And the interesting part, as I am telling, that as the measurement outcome of Alice is completely random, so the key established is completely random. And this is ideal for this encoding of the system. But now the main important question of eavesdropping comes, that if someone is eavesdropping and try to get the knowledge of this key that is getting shared between Alice and Bob. Here remember one thing, in classical scenario what happens, whenever this eavesdropping happens, neither the party that is sending or the party that is receiving, they know that whether eavesdropping happens or not. When I'm telling quantum mechanical cryptographic protocol is secure, this is secure because we can check that whether there is any eavesdropper present or not. And that is important, that if eavesdropper is present, then they will know that there is an eavesdropper present, so they will immediately abandon their process, and then they will again start over. And remember, what I am telling in classical cryptography also is that in the classical cryptography, basically, although by using the existing classical computers, it is very difficult to break, but using quantum computers that will be easy. But when I'm using quantum cryptography, even if you use the quantum computers, this cannot be breaked, because of the reason that any eavesdropper is present or not, that can be easily checked. So as I'm telling, that Alice can use any polarization, any two polarization measurements, either say along some direction A alpha or along some direction beta. And whatever direction they are choosing, or this Alice is choosing, all these directions, basically they will always put an anti-symmetry result between Alice and Bob. That means if Alice gets an up, Bob will get a down, and vice versa. But now Bob is not choosing direction alpha and beta, but she is choosing direction beta and gamma. And remember, these directions alpha, beta, gamma, these are also known to the eavesdropper. And this beta, this is basically common, and this is identified as the preferred basis 0 or 1. And other directions are just to check whether this eavesdropping is happening or not. So as we are discussing in terms of photons, you can discuss with any other two-level systems. So here basically we are considering some polarization parallel to analyzer axis corresponds to +1, and if there is a polarization angle orthogonal to the analyzer axis, then that will correspond to a -1 result. So if theoretical, if theoretically one assumes that every photon carries pre-assigned values determining the outcome of the measurement on each of the photon pairs, it follows that the probabilities of obtaining +1 on both sides, they obey this particular probability, and then this probability will be always has to be greater than equal to 0. But this quantum mechanical prediction for these probabilities with some arbitrarily analyzer settings and measurements is given by this value. And remember, the moment you have this value, this sine half of sine square theta a minus this capital theta b, and you put these analyzer settings in these three values, alpha is equal to -30°, beta is equal to 0°, and gamma is equal to 30°, with some preferred axis, that will lead to this. And remember, this is becoming negative. See, in the previous case, I told that if we have this any classical system, then these probabilities will be always positive. But there is a quantum mechanical state along which a particular set of analyzer angles where this quantum mechanic, where this result, it is getting out to be negative. So basically what Alice and Bob they will be doing, they will be putting their analyzers randomly between these settings. Whether Alice will be using -30°, 0°, and Bob will be using 0° and 30°. And they will be all operating independently. So 4 possible combinations settings will occur, and on which these 3 settings they will be using to allow a test of inequality. And the remaining combination will allow the generation of keys via perfect anti-correlation. So now the important thing is that if measured probabilities violate the inequality, the security of the quantum channel is ascertained and keys generated can readily be used as more knowledge the eavesdropper gains when he or she intercepts the key exchange, the less inequality is violated.
Dr.
The amount
Anirban?
by which the inequality is violated
Hello?
is a real measure of the security of the key.
Hello, Dr. Anirban?
Yes, please.
It is almost 10:30.
Yeah. So I am just finishing. So it is just,
okay.
just the last of these things. So basically, what here we are doing is that to check whether the eavesdropper is present or not, we will be utilizing this particular result. We are utilizing these 3 probabilities and check the values, and we have to use the values to go as negative as we want. The value is getting less negative, or if it becomes positive, then it is certain that there is some eavesdropper present who tries to gain the knowledge by in between intercepting the keys. So the moment these is violated maximally, or this violated is more negative, it is very certain that there is no eavesdropper present, so they can use the keys to do the work that they want to know. So I think as we have already completed the time, so I think I am finishing the talk here on today's scenario, which is basically we tried to give some amount of information that why quantum entanglement is important, and what we can do in future by using quantum entanglement, by using, say, in terms of cryptography, or using, say, in terms of some quantum computing, which is I am not here presented. Say one of the famous case is something called a Shor's algorithm, which is basically factoring a large number to get the factors of a large number efficiently. But of course, the main important of use of quantum entanglement or quantum computer is to generate new features of quantum mechanics that we are yet to understand. Because what we are doing so far is that we have some classical concept, and using those classical concepts, we try to get whether quantum mechanics do better than those classical concepts or not, say in terms of cryptography, in terms of computation and all these things. But the entire quantum mechanics itself is unexplored, and we are yet to achieve or yet to tap on that vast probability of quantum mechanical systems themselves. So with that, I thank everyone present. And if any question is there, definitely I am very happy to take that.
Thank you, Professor Anirban Roy. Your talk is so exhaustive. We have recorded and it will be transferred to all the participants. And since the time is not there, we will skip the question answer because the next speaker is waiting. And but however, I am very happy that in your talk there is a Hardy's paradox you mentioned. But
Yes.
one Indian fellow, Arun Kumar Pati from Aisharai, also proved one generalized Hardy's paradox in PRL paper in 2018. I read in a newspaper. So we
No,
have
sir. Actually, I wanted to make it more simpler. That's what I did not go into the generalized scenarios.
No. But I understand. So I am very happy that our Indian scientists are also contributing a lot in
Yes,
this.
sir. Yes, sir. Yes, sir.
Thank you, Professor Anirban.
Okay. Okay, sir. Okay, sir.